Introduction to binomial probability. We'll see why the word binomial applies at the end. We're going to motivate it in a different way. Let's assume we have 5 wind turbines, a little wind farm with 5 wind turbines. And what we've observed is these wind turbines are assumed to be all identical in terms of how they work and in particular how often they are broken. And what we observe is with a lot of testing and observation of these in the field, if I just look at one wind turbine, then it's going to work 90% of the time. Just that's the observational history of what we should expect with one wind turbine. But we want to ask a question about the whole group, and there's various questions we can ask. And one of the simplest questions we can ask is, what's the probability that all 5 are working at any given time? Okay, most people go ahead and say, oh, I think that's the probability that number 1 is working, or number 1 works, times the probability that number 2 works, and all the way to the probability that number 5 works. Okay, and that would give 0.9 times 0.9 times 0.9 times 0.9 times 0.9, or in other words, 0.9 to the 5th power. And that works out to be 59% of the time. So these are pretty reliable, and so it's not too much to ask that 5 of them are all running at the same time. It's more than half of the time. Now there's an implicit assumption there. You might want to pause and think, did I make a really important assumption there? I'm going to go ahead and go to the next one, though, and then I'll talk about that assumption, reveal there's a little bit of a something we need to say there. Okay, so that second question is, what's the probability that they all fail or none work? Probably best to say it sort of more positively, not with a no there, in terms of they all fail. Well, a very similar calculation would be it's the probability that number 1 is not working. Let me just say fail. Probably that number 2 fail times etc. Probably that number 5 fail. That's a weird 5, sorry. Okay, so looks like it would be 0.1 times 0.1 times 0.1, which would be a very small number. It's 0.1 to the 5th, and that is 10 to the minus 5th, or it's 10 to the minus 3%, 0.001%. So 1 out of every 100,000 times you looked at this wind farm is where they would all be broken. Not just not going because of the wind, but all be actually out of commission. So really important point is that this is almost certainly dead wrong, really misleading. There's an assumption being made here, and we're going to make this assumption for the purpose of deriving these probabilities, but there's a big assumption in both these calculations, and that was an assumption of independence. And that is the assumption that whatever is causing one or more wind turbines to not work has nothing to do, is not associated with whatever might be affecting the other wind turbines. So in particular, if there is some ginormous windstorm that's way too big and conks all of these things out, it's going to do it to all at once. And the reason, and I see number 1 working, and maybe the reason is something that actually affected all of them. It's not necessarily that this thing directly affected one of the others, but maybe they have some sort of common cause for them not working. So these calculations are really good, really useful, but make an incredibly big assumption, which is independence. So let's keep running with that, but it's very, very important that these kinds of calculations make that big assumption, and that really might not be true in a lot of practical situations. Okay, so we're going to make the big assumption that the failure of any one of them is not associated with the failure of the other ones, and then these calculations are going to be good. So these calculations really work very well and accurately with like dice rolling and things like that, where it's designed physically to be independent, where the roll of one die shouldn't affect another. But I have to say that this, I put it specifically in this physical context to address this issue, is that these guys are going to be approximations, and some of these answers, like especially this idea that it's incredibly unlikely to see them all broken, well, there might be something that broke all of them. Maybe the maintenance guy didn't come by for 6 months and they ran out of oil. Okay, so watch out for that, definitely. Okay, but these calculations, if independence is a good assumption, these calculations are on the money. Okay, most people are pretty good with that. at this point, let's say in the class that I teach. Okay, and then here's where people tend to get confused. What's the probability that exactly 4 are working? Okay, and here's what most people do. They emulate the reasoning. They say, oh, okay, that's exactly 4 working and 1 is failing. So I'm going to say it's the probability that number 1 works times the probability that number 2 works, etc. But now I'm going to change the last one to the probability that number 5 fails. Okay, that would be, we're not correct yet, I have to say, I'll just say right now, that would be 0.9 to the 4th times 0.1 to the 1. This answers a different question, though. Really important. This is the answer to a different question, not the one that was asked. This is a classic example of people putting order into a situation where order doesn't matter. I didn't ask for the probability that number 1 and number 2 and number 3 and number 4 were working, and specifically number 5 failed. And that's what this answers. So this is an underestimate, a pretty radical underestimate of the actual probability that exactly 4 are working. If exactly 4 are working, there are 5 ways that could happen. So the first choice you need to make, and it's going to make this, it's going to salvage this as part of the right calculation. The first choice you have to make is, okay, which one is the one that failed? Or equivalently, which 4 are the ones that aren't working? But it's kind of nice, it's easier to focus on the one that failed. Okay. And that is exactly a standard counting problem. We have 5 slots, and we just want to say, okay, which one is the one that failed, or equivalently, which 4 are the ones that are working. Now, once we make that choice, then it reduces to this kind of problem. Suppose the first 4 are the ones that are working. It happens to be those 4 that are working and 5 that failed. Then this is exactly the right calculation. But what if it's that 1 is the one that failed and the 2 through 4 or 2 through 5 are working? You get exactly the same number. It's just going to be the 0.1 is going to be in the number 1 working slot, or the number 1 failing slot, and then the 0.9s are going to be the other ones. So it's really cool. All that you need to do is it's going to be 5, or really a 5C1 or a 5C4 times that. And this is where the binomial coefficients come in. This is why it's called binomial probability. So you could either say that, and that's saying, ooh, I'm going to focus on the fact that there's 5 choices of the one that can fail, or 5C4. And of course, these are the same number. This is the symmetry of Pascal's triangle, or the symmetry of choose binomial coefficients, however you want to say it. And this is the right answer for this kind of question, where I didn't care which one specifically wasn't working or which ones were working. I just care about the number, the total number that are working, or equivalently the number, in this case 1, that are failing. Okay, so this is the model for all the key calculations for binomial probability, and that's why it's called binomial probability. You've got a choose factor times a success probability to a certain power, namely the number of successes, times a failure probability to a certain power, namely the number of failures. Okay, and this one turns out to be, now, these are both just 5, right, in this case. But in general, you're going to have to actually get the choose coefficients either out of Pascal's triangle or out of a calculator, or just calculate them by hand. This turns out to be 32.8%. We would have gotten a 5 times too small number, very misleading, if we hadn't included the choose factor. So it was about a third chance that exactly 4 are working, which makes sense. We'd expect, on the average, if I saw 100 turbines, we'd expect 90 of them to be working based on this. This is about an 80%, and so it's a little unlucky, but it's not ridiculously unlucky. Okay, so I'm gonna in part 2 of the video, I will show you more examples, but that's really the key thing, and this is the model for the most basic important calculation with binomial probability.